Justin Moore, Ashland College Physics here, and we got a little bit more to do with RC circuits. So what else, you may ask? Well, what happens if we want to discharge a capacitor? So if we took a system with a charged capacitor, what really controls how fast it's discharged? And well, it's going to be the resistance in the circuit. Much like its charging behavior depended on its resistance and the capacitance, so does its discharging behavior. So when I look at discharging a capacitor in an RC circuit. So what we're going to do is we are going to remove the source potential. We don't want a source potential there anymore. We want to bypass that or just have it removed from the system, much like we did with this camera, if you remember. So how long it takes to charge depends on the internal resistance inside. There's a resistor that controls that, and the capacitance of the capacitor. I can charge it up. Eventually, it's fully charged. And then what? Well, now I can discharge it bypassing the voltage source because I'm not pressing down on the button anymore. No more voltage source connected to it, and I just discharge it through these wires, which have very low resistance, especially compared to the resistor that's inside this camera. The resistance of these two wires is under an ohm. So what's going to happen when I discharge it? It discharges really, really fast because I don't have that much resistance that ultimately obstructs the current. There we go, fused together. Anyways, that's what we've got going on. So this is what we want to look at. An initially charged capacitor. Capacitor is initially charged. Discharged through some resistance, we'll just say through a resistor. So we can take this circuit and say, let's just put a switch right here. Switch is open. We can take ourselves a resistor, a capacitor. That's all dandy there. There it is. So no source potential, we remove that. And what we want to be able to do is still utilize some things that we know. This is how it was before, right? We've got a plus, minus, plus, minus. And well, right now there's no potential difference across the resistor, but we're going to keep this and then something else falls out of this. So this is just as if we've just removed the source potential and we keep the sign designation. Nonetheless, close this, T equals 0. Close, and then what happens? Well, what can we do with this? Well, we can still go back to Kirchhoff. By Kirchhoff, we have to have the potential difference across the resistor and the potential difference across the capacitor add up to be equal to 0. So if we've got a plus plus or minus minus, doesn't really matter which way you look at it, minus minus plus plus. I'm just going to write it as plus plus because it's a little cleaner looking. Delta V sub R of t plus delta V sub C of t is equal to 0. So you may say, no, it's minus minus. I multiply both sides by negative, and I still got the same expression. So that doesn't matter. So what do we do with this? Well, what we can do with this then is say that delta V sub R of t has to be equal to negative delta V sub C of t. All right, what can we do with this? Well, we've already said before that delta V sub R of t is equivalent to R times I of t, current. And delta V sub C of t, well, that has to be equal to Q of t divided by C. There's a negative sign out there in front, negative Q of t divided by C. Well, what can we do with this? Well, let's move the R over to this side, and we can write this then as I of t is equal to negative Q of t divided by RC. All right, and then we can take one final step with this and say, well, I of t is dq by dt. That's right. So I'm going to write it over here. We got dq, dq of t by dt, first time derivative of charge accumulation, is equal to negative q of t divided by RC. All right, so what does this say? It says, hey, you take a derivative of a function and you get that same function back, but there's a negative of a constant out in front of it. So you get a negative constant factor times that function again. Can you think of any functions that you can take one derivative of and you get that same function back, and possibly a constant as well? And that's right, exponential function. You take a derivative of the exponential function, you get the exponential function back. So what happens if we tried some sort of exponential function regarding this? Well, we need that we get a negative sign, a negative 1 over RC out in front. So maybe it's a little bit easier to see if we say that dq by dt is equal to negative 1 over RC times q, where it's inferred q is a function of time. So we take a derivative, we get this term back, and then we get the original function again. So let q then be equal to, let's say, a times e to the negative t over rc. Say, well, is that what you want it to be? I said, yeah, at least we have something that's of the form, right? Hey, we take a time derivative of this, dq by dt, and we've got ourselves equal to negative a over rc times e to the negative t over rc, which is equal to negative 1 over rc times a times e to the negative t over rc, which is this right here. This is q. So this is a solution for that differential equation right there. Really, really easy to extract solution. The question becomes, well, what does A have to be? So we're going to figure that out. We know, well, what are we looking at here? We're looking at dq by dt, which is what? That's right, that's the current. Current as a function of time. So we've got that I of t is equal to A divided by RC times e to the negative t over RC. Well, what does this tell us? We must have that at I of t is equal to 0, we should be getting back our maximal current, right? Which in this form is just A over RC. That has to be equal to I max. Right when we flip the switch, most of the current, just like we had in the charging, most of the current right when we close the switch, and then as time goes on, less and less. That's okay. So what does that mean that A has to be equal to? Well, that means that A over RC has to be equal to I max, which means that A is equal to R times C times I max. A is equal to R times C times I max. Well, what is I max equal to? I max can be equal to E over R. So we've got that A is equal to RC times E over R, which is equal to EC. Great. What's E times C? Well, again, C is equal to Q max divided by source potential. So E times C is equal to Q max. And we could have already kind of guessed that, not guessed, but already put that in there. That has to be the case, but that's okay. We come find it out anyway. So we got ourselves that for the discharging case, that Q of T is equal to negative, oops, let's just Q max, sorry. Q max times E to the negative T over RC. there's the charge accumulation on the plates of the capacitor. T equals 0, fully charged. As time goes on, we got exponential decay. Most of it comes off really quick, and then as time goes on, the rest kind of leaks off. But it really depends on what is the capacitance and what is the resistance and what is the capacitance. And that's pretty much that. So we can get the charge accumulation as a function of time. We've already got the current as a function of time right here. I of t is equal to, well, there's a negative sign. That's where I'm leaving something out. dq dt, there should be a negative sign right there. My apologies. Negative sign for that, not for q. So the negative sign gives us negative I max times e to the negative t over RC. The negative sign here is really just saying, hey, it's the discharge current. It's in the opposite direction as when it was charging through the resistor. Now it's being discharged through that resistor, and that's just an oppositional sign there. So a directional sign, I should say. We still have exponential decay regarding the current, exponential decay regarding this, and well, we have to have exponential decay regarding the potential differences as well. Because it's coming off of the capacitor, going through the resistor, both of those decay both down to 0. You add them up at any given moment in time, one's positive, one's negative, it equals 0, and as time goes on, there's no more current in the circuit, there's no more charge accumulated, and the terminal kind of state of the system is 0 for everything. No current, no potential differences, no charge accumulated. Everything decays exponentially in this case, which all falls out of Q of t and I of t. All right, so that's just kind of that. It's interesting, it's cool. I think the charging's a little bit more elaborate, but discharging's something to look at too. And just, yeah, just know what's going on, whether it's charging, discharging, and treat it as it needs to be treated. All right, I will bid you all a farewell, a good day, and I just say stay charged up. Take care.